Guillermo del Toro's 2013 sci-fi monster thriller asks the question, how do you fight a monster? The answer? You create your own. Pacific Rim follows the war between colossal, interdimensional monsters known as the Kaiju, and humanity, who have constructed skyscraper-sized Jaegers to fight them. Today, we'll analyze one of my favorite scenes from Pacific Rim and determine the force and energy behind the Jaegers. The clip starts with the Kaiju and the movie's main Jaeger, G-Danger, charging at each other. G-Danger leaps into the air and lands the first hit, followed by a hook and an uppercut, stunning the beast. G-Danger then charges up an elbow rocket and hits the Kaiju with a devastating powered punch, sending it tumbling backwards. Before calculating the force and energy of the punch, we first need an estimate of the colossal robot's mass. In this clip, we can see workers in the background next to G-Danger's head. Comparing the height of the workers to the robot's head, we can see that the head, top to chin, is roughly 6 workers tall. Assuming the workers are 6 feet tall, it gives us an estimate of 36 feet for the height of the head. Next, with this image of G-Danger, we can see that it is about 9.5 head lengths long, for a total height of 342 feet. Scaling this to a human, we can see that G-Danger is approximately 57 times larger. Now using the average volume of a human, which is 65.2 liters according to a Harvard study, and multiplying it by a factor of 57 to the power of 3, following square cube law, we get a volume of roughly 121 million liters. Converting this to cubic meters, we get a volume of 12,100 cubic meters. Next, we use the density of pure iron, since the Jaeger consists of a solid iron hull, no alloys, and multiply it with the volume to give us a final mass of 9.52 times 10 to the power of 7 kilograms, or a little over 95,000 tons. For scale, that's equivalent to the weight of 226 international space stations. Force of punch. To calculate the force exerted by the elbow rocket punch, we need to calculate its speed. We can see that in the clip it starts from rest with the elbow at full retraction at the level of the head and travels about halfway to full extension before making contact with the Kaiju. If we take the proportions of a human and apply it to G-Danger, we can see that from full retraction to full extension from the elbow is exactly 1 arm's length. If we apply these proportions to G-Danger, we get an arm's length equal to 144 feet, or 43.9 meters. Finally, to estimate the distance traveled by the elbow rocket, we divide the arm's length by 2, since the arm only travels halfway to full extension before making contact with the Kaiju, and we have a final result of 22 meters. I timed the course of the elbow rocket when it is released to the moment it makes impact, giving us a value of approximately 1.3 seconds. Using the velocity formula, we know that the final velocity is equal to the distance traveled divided by the time elapsed, which gives us a result of 16.9 meters per second. We can then use one of our kinematics equations to find the average acceleration. Using the formula, A average is equal to V final minus V initial over delta time. Substituting in our values, we get an average acceleration of 13 meters per second squared. To find the mass component of the equation, we can assume that G-Danger has a body part mass ratio proportional to that of humans. Because the mass that is accelerating is simply the forearm and hand, the mass of the load will be about 2.52% the mass of the Jaeger, equating to 2,399,040 kilograms, or 2,399.04 tons. Putting this into the fundamental force formula gives us a value of 31,200,000 newtons of force. For reference, that is almost equivalent to the force of a Saturn V rocket, or an Airbus A320 impacting the Kaiju's face faster than the speed of sound. Here's a quick free body diagram of the rocket punch as it impacts the Kaiju's face. As we can see in the first clip, the fist comes to a complete stop upon impacting the Kaiju. Therefore, net force in the x direction would be 0. In the y direction, the force of gravity pulling the fist towards the ground is counteracted by the force applied by the body keeping the arm up. so the net force in the y direction would also be 0. Next, to calculate the energy possessed by the rocket punch, we use the formula mechanical energy is equal to the sum of kinetic energy plus potential energy. Starting with kinetic energy, we can use the formula Ek is equal to 1/2 times mass times velocity squared. However, as we can see in the scene, the fist is angled downwards. We have to account for this angle in our kinetic energy formula as it will affect the overall velocity. I estimated the angle to be roughly 30 degrees by using the containers in the background. Separating the velocity into its x and y components and multiplying it by the sine or cosine of our new 30-degree angle, we can get our new velocity values for our kinematics equation. Ek is equal to 1/2 times mass times velocity y squared plus velocity x squared. Our new formula yields us a kinetic energy value of 341,338,410 joules, or 3.41 times 10 to the power of 8 joules. Moving on to potential energy. To calculate the potential energy of the elbow rocket, we need 3 components: the mass, the gravity constant, and the height above the ground. We have the mass and we know the gravity constant, so all we need is the height. From this clip, we can see that the arm is on about the same level as the head. Using our previous calculations for scale, we can estimate that the fist is approximately 92.5 meters above the ground. Using the potential energy formula, mass times gravity times height, we get an energy value of 2,177,820,000 joules, or 2.18 times 10 to the power of 9 joules. Going back to our mechanical energy equation, we can add the two values up to get an energy value of 2.52 times 10 to the power of 9 joules, or a little over 2.5 billion joules. If you were to convert that energy into kilowatt hours, you would be able to power the average house in Ontario for 23 days. Conclusion. With modern technology, a Jaeger like G-Danger would not be possible. Because of the enormous weight of the Jaegers, they would collapse under their own weight when in motion or in battle. Following the principles of the square cube law, the surface area of the feet would not be great enough to support the weight of these gigantic machines. There is no currently available material or technology capable of withstanding the strain which would still be flexible enough to move and fight. Powering such a colossal load to move and flex so rapidly is also simply not possible with technologies currently available. Nonetheless, the concept is fascinating to entertain, and the movie is overall a thrilling experience. Just don't watch the sequel.